This video is part of the course Forensic Physics: How Science Solves Crimes in Court, an educational initiative presented by the Physical Sciences Consultorium. Through this course, we explore how the laws of physics are applied to forensic evidence and how scientific reasoning supports legal decision-making, especially where science intersects with law and society. In this episode, we turn our attention to sound. Sound is often treated as secondary evidence, yet it carries precise physical information. Every sound is a physical signal governed by laws of motion and wave propagation, not merely a recording or a human perception. Forensic acoustics studies how sound is produced, how it travels through space, and how it is ultimately recorded by devices. It treats sound as measurable motion in a medium, allowing physics to constrain interpretations of events such as gunshots, shouted words, or sudden impacts. At its most fundamental level, sound is a mechanical wave consisting of pressure variations that move through a material medium. Unlike light, sound cannot travel through a vacuum. It requires matter, such as air, water, or solid structures, and each of these media alters how sound propagates. In air, sound travels at a finite and approximately constant speed under normal conditions. This speed depends on physical factors such as temperature and composition. Because sound does not arrive everywhere simultaneously, it naturally carries timing information. This finite speed of sound is central to forensic acoustics. When a sound is produced, it reaches different locations at different times. These time differences allow investigators to constrain distances and reconstruct sequences of events, although never with perfect precision. Real environments, however, are far from ideal. Sound rarely propagates freely without interference. Walls, buildings, terrain, and objects reflect sound, while other materials absorb or scatter it. These interactions shape what is ultimately recorded. Echoes and reverberation are not noise or errors, they are physical consequences of reflection. In enclosed spaces, sound can persist even after the source stops, and this persistence encodes information about the environment in which the sound was produced. Outdoors, sound spreads and weakens with distance, while wind, temperature gradients, and terrain can bend sound paths. These effects mean that forensic recordings are often mixtures of direct sound and reflected components. Because of this complexity, forensic acoustics emphasizes physics over perception. Human hearing is not a reliable measuring instrument. Loud sounds may seem close, and quiet sounds may seem distant, but physics corrects these intuitions by grounding interpretation in measurable quantities. One of the most important forensic uses of sound is timing. Sound effectively acts as a clock. If the same sound is recorded at multiple locations, differences in arrival time can be measured and used to constrain the possible location of the source. Even a single recording can contain timing information. Reflections introduce delays that depend on distances to surrounding structures. However, these delays only constrain ranges, not exact positions, because environmental details are rarely known perfectly. This unavoidable uncertainty does not make sound evidence useless. Instead, it defines how sound must be used. Acoustic evidence constrains what is physically possible, rather than providing absolute certainty. Gunshots are among the most common applications of forensic acoustics. Importantly, a gunshot is not a single sound but a sequence of acoustic events. Different components of the event may propagate differently and arrive at different times. Recordings often capture only part of this acoustic sequence. Consumer devices such as smartphones compress audio, filter frequencies, and distort timing and amplitude. They are not designed for forensic precision. For this reason, forensic acoustics must interpret recordings cautiously. Audio files are not raw physics. They are signals shaped by devices, environments, and recording conditions. Physics must interpret them, not assume them. At this point, a critical distinction must be made. Sound recordings represent signals, not events themselves. They are indirect representations that require physical modeling and careful interpretation. Audio recordings are increasingly common in forensic investigations, but their use requires careful physical interpretation. Every recording is shaped by the microphone, the recording device, and the environment, and these factors must be understood before any conclusions are drawn. Sound recordings are signals sampled in time. They are converted into digital form using specific sampling rates and bit depths, which limit the amount of information that can be preserved. Compression algorithms further alter the signal, often discarding details that are perceptually less important but physically relevant. Background noise is another critical factor. Real recordings almost always contain overlapping sounds, including traffic, wind, voices, and electronic interference. Separating meaningful signals from noise requires careful analysis and introduces uncertainty. Synchronization presents additional challenges. Different recording devices rarely share a common time reference. Even small timing offsets can significantly affect distance and localization estimates, especially when sound is used as a clock. Forensic acoustics therefore relies on models rather than direct observation. Analysts compare recorded signals with expected acoustic behavior based on physics, testing whether a proposed scenario is consistent with the data. This approach emphasizes consistency, not certainty. Multiple scenarios may fit the same recording, and forensic acoustics must acknowledge this explicitly. Overinterpretation is one of the greatest risks in audio evidence. In court, acoustic evidence is presented cautiously. Experts focus on explaining physical principles rather than asserting conclusions. Visual aids such as waveforms, timelines, and diagrams are often more effective than equations. Expert testimony must clearly state assumptions, limitations, and sources of error. This transparency allows courts to evaluate the strength of the evidence without being misled by technical complexity. It is also important to distinguish scientific analysis from enhancement. Making a sound louder or clearer does not necessarily make it more accurate. Enhancement can introduce artifacts that misrepresent the original signal. Forensic acoustics does not determine intent, identity, or motive. It addresses physical questions such as timing, consistency, and plausibility. Legal interpretation remains the responsibility of the court. This episode reinforces a central theme of the course. Physics constrains reality. It does not tell stories, but it limits which stories are physically possible. Sound, like motion and heat, follows natural laws. When used responsibly, it can support justice by clarifying what could have happened and what could not. This course is presented by the Physical Sciences Consultorium, which is committed to rigorous, responsible science education and public understanding of how physics informs real-world decisions. If you find this course valuable, please like, share, and subscribe to support the continued development of open-access educational content. In the next episode, we will turn to digital traces and sensor-based evidence. We will explore how physics underlies modern forensic technologies and the limits of what digital data can reveal.